Hello, y'all, and welcome to lesson 86 of my DP chemistry curriculum. Today we're going over reactivity 2.2.10 and 11. It's going to be a bit of a long one. So in 2.2.10, we're talking about the order of reaction with respect to a reactant is the exponent to which the concentration of the reactant is raised within the rate equation. Furthermore, the order with respect to a reactant can describe the number of particles taking part in the rate determining step. So we're going to talk about order with the rate determining step. Furthermore, the overall reaction order is the sum of the orders with respect to each reactant. So an order of one plus an order of one is an order of two. All right, with that, we'll be able to sketch, identify, and analyze graphical representations of zero, first, and second order reactions. Furthermore, in 2.2.11, we're going to talk about the rate constant K is temperature dependent and its units are determined from the overall order of reaction. We're more going to focus on the second part, as we know, as part of K changing the way that the reaction takes place, or temperature changing the way the reaction takes place, K must therefore also be dependent on temperature. Anyways, with that, we'll be able to solve for the units of K. So by jumping right in, when we talk about any rate expression, we learned in the last unit that the concentration of reactants, so we can just represent that as concentration of reactants, will change the rate, change the rate. And we know that already, and the amount that it changes it differs. The amount changed can be determined by the exponent in the rate equation. So we refer to that exponent specifically as the order of reaction. All right. So for example, if we have some rate where we have some rate is directly proportional to the concentration of a reactant A, we would say this is an order of one in respect to A. Or sorry, not the concentration of A, just order of one in respect to the reactant A. Furthermore, when we had a rate that was proportional to A squared, that would be order of two in respect to A. So if we therefore then look at any reaction, the order of each reactant summed is equal to the overall order. So a quick example of that is if we then have some maybe bimolecular reaction where the rate is proportional to A and B, that would be an order of two. And so we can just tell from these exponents, exponent one, that sums to be an order of two. If we had something maybe termolecular where this was maybe A squared, then it would be an order of three. But that's all right. We don't really need to get into that because it's kind of obvious from the so far. Now, what can we actually do with these proportionalities? Well, we can convert this into the actual rate equation. So we can convert to rate equation of reaction by using a rate constant. So once we put in a value that converts this proportionality right here into the actual equation, so something that we can multiply by some constant k, then instead of a proportionality, this becomes an equals. And so what I'm saying is we can now take this equation up here, use a constant k, and it becomes rate is actually equal to the constant. times A times B. And that is now our rate equation. So this is how we relate the rate expression to the actual rate. So that K relates rate expression to actual value of rate. We can see that even with this equals K times is just the equivalent of a proportionality. This is some constant that shows us how rate is proportional to A and B. So this is just math at this point, but that is how we get our actual rate by using the rate constant K. Now that we have this actual equation, we can even represent this graphically. So we can represent our order graphically. We'll do that here, representing fix that S. Well, that S is just getting worse. So representing order and rate graphically. Now, we've mentioned before that finding these is usually experimental, and we can actually do this by looking at concentration versus time graphs. So we can find order through concentration of something, some reactant X versus time graphs. Now, there is an issue between order 1 and 2 graphs are near identical. And we'll see that in a minute. Therefore, we can, instead of using concentration versus time graphs, we can use rate versus time graphs to identify order. And we can explore this as we go through it. So let's just start with a 0th order reaction. Now, 0th order is when our rate is not affected by the concentration of reactant. It has, so rate is not affected by concentration of reactant. In other words, rate is equal to K, so now we're using the actual rate equation, times our reactant X to the 0th power, which is just equal to K, because X to the 0th power is 1. When we look at the two graphs that we can make from it, I'm going to make some nice graphs that I can just copy and paste throughout this. On our left graph, we're going to be talking about concentration of reactant X versus time. On our left graph, we're going to be looking at rate versus concentration of our reactant. So in 0th order, where the concentration changes over time, we just know that our concentration will decrease over time. Now, before I do that, actually, I'm going to try and copy this so I can just reuse it. All right. So in our first one, we know that the concentration will decrease over time, and it'll look pretty linear because our rate isn't changing, meaning the concentration is going to go down at a steady rate. We also know that because rate is not being affected by the concentration, as concentration changes, rate will remain constant. That's what a 0th order reaction describes. Now, when we move over to 1st order, we know that rate, quite simply, is equal to our constant times our concentration of X, and this is proportional. We know that rate is changing over time. So we're going to take our graphs here. And we know that because rate is changing in a directly proportional way to x, I'm actually going to start over here um, on my right graph. That's going to be linear. This is a directly proportional or linear relationship. And as that rate increases with a higher concentration of x, conversely, when we look at our concentration over time, it's going to start with a quick decrease and smooth out. So this is our first order reaction. When we move over to our second order reaction, we know that rate is equal to our constant times our concentration of our reactant, in this case, x squared. When we look at our two equations, we'll use the same two graphs. Again, I'll start with my rate versus concentration. This is now a squared relationship. You know this as a parabola. I'm going to draw that a little nicer. I'll still try and draw that nicer. There we go. And then so this is what our reaction looks like. We can very much see a difference between our second order, first order, and zeroth order in our rate versus concentration graphs. This is usually what the DP will ask you to differentiate the order based on those graphs. Now, when we look at our concentration versus time graphs, which are usually what we're using when we're determining things like equilibrium, we look at how the concentration changes over time and we wait till it steadies out in an equilibrium reaction. But when we bring it over here and when we're talking about a second order equation, it's going to look near identical to our first order. The only difference is we actually have a steeper curve. So when we put them next to each other or we superimpose them, for example, if I go ahead and superimpose this one over the other, you notice a steeper curve. However, from a distance, it is difficult to actually tell that they are any different. So this is why, as I mentioned before, we need concentration or rate versus concentration graphs to determine the order graphically. All right. Now, as we move forward talking about order, let's go ahead and look at reaction mechanisms. So when we have multi-step reactions. So this will be order and reaction mechanism. We know that our order must be determined experimentally for an overall reaction. We did a little bit of practice in that in lesson 85 as we looked at the change in rate versus the change in the concentration of our reactants. But this is not true for elementary steps. This is not true for elementary steps. So when we're looking at a multi-step reaction, we don't have to worry about the full reaction to figure out order. So we already know that rate is determined from slowest step. That is what we would refer to as the rate determining step. Therefore, order is also determined from this step. So when we look at an elementary step, we can use that to determine both the rate and the order. So I think the best way to do that is through an example. So in this example, we're going to look at the reaction 2A reacts to form 4B plus C. And we'll break it down into 3 steps. So step 1 will be A reacts to form B plus D. Then we'll look at step 2, B plus D. both of those being intermediates, will be B plus C plus E. And then on the last one, step 3, we're going to look at A plus E, and this will form our 2B. And so if we look at this overall, this B and this B, sorry, B and D will cancel with B and D. C C will remain, E and E will cancel with E and E. And overall, we will have our entire reaction. Now, when we do this, we have to figure out which step is rate determining. So in this example, step 1 will be slow, step 2 will be fast, and step 3 will be fast. So the first thing we need to do is determine that our rate determining step is our first step. So with that information, we're only going to look at step 1. So as we look at step 1 being our rate determining step, we will find that our rate is going to be equal to our rate constant times the concentration of A, our only reactant that determines rate. In this case, we know that this is an order of 1. So for multi-step reactions, it's actually quite simple. We can now just kind of create a chart that determines the order of any reaction from our elementary step. And if we have A reacts to form our products, we know that this is going to be unimolecular with one reactant. So that'll be our molecularity. And our rate law will just be rate is equal to K times the reactant, or the concentration of reactant A. Now, if we have 2A makes our products, this will be bimolecular, and our rate is equal to K A squared. If we also have A plus B makes our products, this will be also bimolecular, and our rate is determined by K, reactant of A, concentration of reactant B. Now, we also mentioned previously that it's very odd for our elementary steps to be termolecular, so we're just going to leave it here at these bimolecular elementary steps. Again, this is only when first step is rate determining. All right. So what if first step is not rate determining? So first step is not rate determining. What do we do? This one's a little more complex. So let's go ahead and look at a new example. Always better with examples. If we have A plus B reacts to form AB, and then A plus AB reacts to form A2B. And in this case, our first step is fast and our second step is slow. So in this reaction, we see that the second step is rate determining. So we know from this that our rate is going to be equal to K A AB, which seems simple enough. But the problem with this is that the creation of AB is actually a function of A plus B. So AB is actually determined by the rate of A, concentration of A times concentration of B. So we're actually going to substitute that in, and therefore our new rate equation is going to be equal to K A, and then AB is a function of A and B, which can be rewritten as K A squared B. From this, we find that our reaction actually has an order of 3 overall. It is an order of 2 with respect to our reactant A and an order of 1 with respect to our reactant B, but overall, our entire rate or reaction has an order of 3. So if the first step is non-rate determining, then you must therefore move on and take what the other reactants are and take those as a function of their own individual equations. So it becomes a little more complex, but you will never have to do anything more complex than this reaction anyways. All right, moving on to 2.2.11. We're going to talk about the units of K. How do we determine them? Well, the thing is, they vary in respect to order. And this kind of makes a little bit of sense. If we look at the equation or the rate law, rate is equal to K times some reactant X. We know that rate has a units of mole, decimeter, cube inverse, second inverse. We know that X, or our concentration of X, has units of mole, decimeter, cube inverse. So in this case, using dimensional analysis, K must have units of second inverse. And this is an order 1 reaction. However, if we move on to something that's order of 2, if we have rate is equal to K X squared, we still know that rate is going to be mole, decimeter, cube inverse, second inverse. But now our concentration of reactant X is now squared. So we have mole, decimeter, cube inverse, and that whole thing is squared, meaning we have mole squared, decimeter to the 6th inverse. So in this case, you can use dimensional analysis, you can use a little bit of algebra, but we know that the units of K, if we want to go the algebraic rate route, are equal to the units of the rate divided by the units of the concentration of X squared. So we can plug this all in, but really what I like to do is just look at my concentration and determine how do I take that and turn it into this. So for one, I'm going to need to add a second inverse because the rate is always per second. And then I have to cancel 1 mole. So I'm going to add a mole inverse. And I have to cancel 3 of our inverse decimeters. So I'm going to do decimeter cubed. In this case, that's the order for rate on our second one. So for the last one, try this yourself. If we have our example, which is an order 3, and rate is equal to K A squared B. Find the units of K. K units equal. So go ahead, pause it, try and figure it out yourself. All right, now that you've come back, quite simply, all we have to do is cancel out 2 of the 3 moles. So we're going to do mole squared. We have to cancel out 6 of the 9 decimeter inverses, so decimeters to the 6. That 6 looks a little odd. And then we still have to add our inverse second. And so our units of K are going to be mole squared mole squared inverse decimeter to the 6th seconds inverse. All right. Well, I hope this helps you understand order of reaction, units of K, graphical representations of order, and all that good stuff. And have a great day.